Welcome. Today we are going to see how to do buffer overflow attack. So first let me show my laptop configuration. This is my OS 19.04, which is one of the latest OS. And this is my kernel version, and this is x86 64-bit version. Okay. Now we will see what happens when we post more data than the allocated buffer size. For that, let us take an example program. Demo.c. This program contains main function which is calling getInput. Inside that we have declared a buffer of size 8 bytes and gets, which is going to take the input from user, and puts, which will print the input on the console. And there is another function can never execute, which contains a printf statement of I can never execute. Actually, we can never execute this function because we are not calling this function from this program. Okay. Now let us quickly compile and run this program. We are seeing usual warnings. Doesn't matter. Let's move further. It is prompting the input. Enter some random input. Okay, as of now, there is no problem. We have allocated buffer size to 8 bytes. So let us see when we enter more than 8 bytes, what will happen. We can see stack smashing detected error. That is because in modern operating systems, there are many privacy settings which can protect the stack. One of that is ASLR, which is address space layout randomization, which will change the buffer address every time. So that is like protecting the stack. Then there are many flags which is also protecting the stack. We need to disable that so that we can avoid this stack smashing detect error. First, let us check what has been said in the ASLR. Command is this one. Okay, it has set as 0 already, which is disabled. If it is 2, it is enabled. So now we will recompile the program by disabling the flags. Now enter. See now, even though if we enter the data which can exceed the size of buffer, it doesn't throw any error. Okay. Now let us see what happens inside the memory when we enter more data. So quickly let us load the program in GDB. Okay. Debug the program. test out this. Set a breakpoint on line number 12. Let's run this program. Now examine the stack. For that the command is ss to examine. Then number of words to examine is 16. Then in hexadecimal words, specify the register name or space. Okay. Now we can see this is the written address. This is old EBP value, and this is the allocated space for the buffer. So we can verify this by disassembling the main function. Okay. After the get input call to get input function, we have this address which is written address 40117B. So which has been set here 40117B. This is written address, and this is old EBP value. And in 64-bit, all the addresses are in the form of E8 bytes. So this together contains as an address, this together as an address. So this is 4 bytes, this is 4 bytes. In 64-bit, this is the form of addressing. Okay. Now let us run the program. Okay, sorry, I have run it already. Let me step through the program. It is waiting for user input. Just enter the data more than the buffer size. And now examine the stack again. See, we can see it has override the old EBP value also, and the return address has also been changed. Now step through the program. We can see this. See, this is error because the GDB is asking in the place of return address something else is there. What is this? So it is asking me that. So now it is showing error. Okay, fine. Now let us disassemble can never execute, so that we can see whether we can execute this program without calling this. Okay, this is the starting address of this function. Quit this. Now we can give the input while running also. The way to give the input is just put 16 bytes of some random data. The first 8 bytes will be copied here, and next 8 bytes will be copied here. And this location we need to give the starting address of can never execute. We need to give this address in the reverse order and in hexadecimal. 3, 2. See, we have executed. I can never execute. Okay. Now we have learned what will happen when we pass more data into the buffer than the allocated size. Then what happens inside the memory, all those. So now we are going to see how to exploit this buffer overflow. Okay. Let us see assembly program. So how we are going to exploit the buffer means we are going to take this assembly program and convert this into machine instruction byte, which will produce shell code. After getting that shell code, we can put that inside a C program and we can call it uh, this won't exploit the buffer. This is a normal program through which we can execute bash shell script. And by using the same shell code, we can exploit the stack. We will see how to do that. So first I will explain what this assembly code does. First I will say how we need to call the system call, the format of system call. So first the every system call consists a number. So in the AEAX register, always we need to load the system call number, and in the EBX register, we need to load the first parameter, and in the ECX register, we need to load the second parameter. In EDX register, we need to load the third parameter, and so on. So now let's quickly see this program. So jump line, as soon as it reaches the jump line, it will jump to the line label. So next is call address. So it will go here, this address label, but before that, on the stack pointer, sorry, the instruction pointer will push the this string. This is a written address, and after that it will move here. Then the next line is pop esi. So the last thing which was pushed into the stack is bin sh string. So now we have taken out from the stack and copied into esi register. Now move esi 0x 08 ESI, which means this is adding 8 to the ESI, which exactly means 8 locations ahead of ESI. We are copying the content of ESI. Then XOR EAX EAX. When we are doing XOR operation of the same content, it will produce 0. So what happens here? We are copying 0 into EAX register. Now this line move EAX comma 0xC ESI. This C is hexadecimal, which is uh, 12 in decimal. So which is 12 locations ahead of ESI. We are copying the value of EAX. Okay, and now move EAL comma 0x7 ESI, which means now in the EAX register 0 is there. We are appending the 0 into this one bin sh string, which is there on the location 8 location ahead of ESI. We are appending that. Now it will become as an array, and now move 0xb comma EAL. B means in decimal it is lemon. So we are moving lemon into EAX and move ESI EBX. In ESI we have this string. We are moving this string into EBX, and now load effective address. LEA is load effective address of 8 locations ahead of ESI. We are loading that address into ECX, and we are loading 12 locations ahead of ESI into EDX register. So in this location we have array of bin sh and null, and in this location we have 0. Now we are calling the interrupt. So basically in the last 4 lines what happened, we have moved B, which is 11. 11 means the system call number execute BE. So we have loaded that system call number. So the format of execute BE system call is it contains 3 parameters. The first parameter is the file name. And the second parameter is arguments, array of arguments. The third parameter is null pointer. So now we have loaded that only. We have loaded the system call number on EAX, and EBX we have loaded the string, and ECX we have loaded the array of argument location, and on EDX we have loaded the 0. and we have called the system call. Okay, so what happens here? This file name is bin/sh, which is going to execute bin shell script. Okay, after executing that, when we are coming out here, these lines, let us see what it does. So XOR EBX EBX. It is when we are doing XOR of the same thing, it produces 0, so we are copying 0 into EPX and we are moving that 0 into EAX and we are incrementing EAX. So now EAX contains 1, EBX contains 0 and we are calling interrupt. So system call 1 is exit system call. So now we are exiting this. Okay, so now let us assemble this program. We have saved this program as aleph.es. This here I can show you this program, and this is the format of assembly language program in 64-bit, and this RSI call this OR. We need to change this OR as OR because in 64-bit system everything is started from OR, and E, when we specify E, we are using the 32-bit location. So if we can use 32-bit also or 64-bit also, or E, both will be acceptable. Okay. Now this is the program. We can assemble this. Now let us link this program. Fine. Now we need to generate a shell code for this, which is machine instruction bytes. For that, we can directly use this object dump utility, or else we can wrap up this assembly code into a C program like this, and we can compile and generate that machine instruction bytes like this also. I will show you both the methods. Both will produce the same shell code. Okay, it has produced the shell code. Now we will wrap up this assembly code into a C code and we will generate the shell code and we will see. Okay, we have wrapped up this program and let us compile this. Clear the screen. Fine. So we have generated the shell code by using object dump utility. We have to take from here, which is jump line. Okay, EB28, the same generated here also. After this, let us see how to execute that shell code, putting that inside a C program. Okay. See here, I have attached all the shell code here in a character array. Let us verify here. EB28 You can see everything is in hexadecimal, EB 28, 5E 48, 5E 48, and go on until 7368. So we can say 7368. Okay. Now next is this one. This is a type of pointer. Sorry, this is a type of function uh, which takes a pointer and returns nothing. And we are passing the address of shell code, and we are casting this as a function pointer which returns nothing. So basically this shell contains this machine instruction bytes, and when we call this shell it will execute this. So now let us compile this and execute. We'll see what happens. Okay, execute this. See, now we are in shell script. Let's verify who am I. See, it is working. Exit. Now we will see how to use this code to exploit the stack. We have added the same shell code here, but the remaining code is little bit different than the old one. Inside the main function, there are two arguments. We are not passing anything here, and we are calling the function foo and passing shell code as the argument. Okay, now we can see here we are taking that shell code address here, and we have created a buffer of size 54 bytes. For simplicity, I have created only 54 bytes because this shell code together forms 54 bytes. So I just created only 54 bytes for simplicity, and strcopy buffer argument. Simply we are copying all these contents into buffer and we are returning. So we will compile this program. Okay. Let us load this into GDB. Debug this. Fine. Let's start the program. Okay. Set a breakpoint on line number 16. Now disassemble the main function and foo function. Okay. We have disassembled. Also check the address for shellcode. For that, print. Okay, this is the address of shellcode. We can also see the content of shellcode. Fine. Now let's run the program. We have hit the breakpoint. Examine the stack. Okay. So now from here to till here, uh, the size allocated for the buffer content, and this is for all EBP value, and this is for return address. So whenever there is a function call in program, first the stack pointer will push the return address into the stack, and then the old EBP value onto the stack. After that, it has allocated the size for the buffer. Now let us step through the program. Now examine the stack. See, now we can see the shellcode is copied here. EB28, 5E, 48. It is in the reverse order, and now until here it has copied everything. And now this is EBP value, and this is the return address. Now let us try to change this return address to point out the shellcode address so that we can execute this shellcode. Why we are putting a long here means in 64-bit every address is in the form of E8 bytes. We cannot put int because the size of integer is 4 bytes. So the size of long is 8 bytes. That's why we are using long here. The value of RBP is 10. I can show you now. So we can see value of RBP is DD10, which is here. From here we need to point here plus 8, and in this location we need to change the address. Okay. Now examine the stack. See, we have changed the return address, which was the shell address of shellcode. Okay. Now step through the program. Now we are in shellcode. Okay. Now look here. Process 5958 is executing new program user bin dash. Okay. It is successful now. So now we will see how to execute this outside GDB. Look at target.c. So when we quickly look at here there are 2 bytes remaining, and here 4 bytes, here 4 bytes, and this 4 bytes, this 4 bytes. Everything together 18 bytes are remaining until return address. So we need to add some padding for these 18 bytes. So I have added /x90 for 18 times here, until here 18 times. /x19 is for no operation. It will do nothing. And then I am appending this address 404040, which is the address of shellcode. I am appending here, and now let us compile this. Successful. Now run this. Okay, we are in shell. Fine, it is working. Inside GDB also, this program will work. You can see first debug this program. Now run this program. See, now we are in shell. So everything is working. Okay. Okay, sorry. Now we have seen what happens when we enter more content in the buffer than the allocated size. Then how we can use that exploited buffer by and how to run some other program by pointing the sorry changing the return address. We have seen that. So that's all. This is how we can do the buffer overflow attack. Thank you.